Ready to go?
Yes.
All right, then let's get started. We're very pleased as our first speaker to have Wanlin Li from MIT, who will be telling us about the Ceresa class and its tropical, topological, and local aspects. And take it away, Wanlin.
Oh, thank you. I hope everyone can see my screen fine. And okay, let me actually hide the floating meeting. Okay, great, perfect. Oh, actually, I should also hide the video panel probably. Okay. Okay. Thanks for the invitation, and I'm very happy to speak here. And today I will be talking about the Ceresa class from a tropical perspective using topological methods for curves over local fields. And this is ongoing work joined with Dan Corey, who is a postdoc at UW Madison, and my PhD advisor, Jordan Ellenberg. So first of all, let me define the Ceresa class for you. So one way to define the Ceresa class is to define it using a cycle class map from an algebraic cycle called the Ceresa cycle. Let's say be a smooth projective curve over a base k with a k point. We can actually, can I ask a question, Daniel? Daniel, can you hear me?
Yes.
Do you see the notifications that are showing up on my screen?
I don't think so, no.
Okay, perfect. Sorry. Yeah, I kept on seeing, sorry. I kept on seeing some notifications from Zoom.
Tune out the notifications. You're doing great.
Okay, thank you. Okay, so yeah, if we have a smooth projective curve over a base k with a given k point, there you can embed your curve into its Jacobian by sending every geometric point p to the linear equivalence class p minus c, or on the other hand, you can also embed it by mapping p to c minus p. So this is the same as I have iota of c, and then I compose it with the -1 map on my Jacobian, because my Jacobian is abelian variety, it has an involution -1. So the image of iota c and the image of iota inverse, their difference is the algebraic one cycle in the Jacobian of my curve. And it is actually homologically trivial. And this is called the Ceresa cycle. The reason called Ceresa cycle is because Ceresa proved that for a generic curve of genus at least 3, this cycle is algebraically non-trivial. And well, it's easy to observe that, for example, if my curve is hyperelliptic, and if the point I'm using to embed is a Weierstrass point, then the iota c and iota inverse c the image will agree, because the -1 map on the Jacobian will just restrict to the hyperelliptic involution as the image of iota c. Thus, this explains that why in Ceresa's theorem, the genus of the curve is at least 3, because curves of genus less than 3 are hyperelliptic. Okay, and since we have an algebraic cycle which is homologically trivial, so using a cycle class mapping in cohomology, we can get a cycle class with coefficients wedge 3 of the first étale cohomology of the curve. And also, by passing to a quotient of this coefficient group, we can actually induce a cycle class of this Galois cohomology that does not depend on the point we choose, only depends on the curve. And actually, it only depends on the rational equivalence class of this Ceresa cycle. So we get a Galois cohomology class where when this class is non-trivial, we know that it shows that this Ceresa cycle is rationally non-trivial. So this Ceresa class gives us a way to start this algebraic cycle. And because the Ceresa cycle is such a natural algebraic cycle, there were lots of previous work on it. And here is just a small list of it. So Harris used the notion of harmonic volume, showed that the Ceresa cycle for a degree 4 Feynman curve is algebraically non-trivial. And recently, also using the harmonic volume method, Eskandari and Morita showed that for degree n Feynman curve, where n has a prime divisor at least 7, the Ceresa cycle is also algebraically non-trivial. And in tropical geometry, Jarkov defined an analogous notion of the Ceresa cycle for a tropical curve. And if the tropical curve has its underlying graph having K4, which is a complete graph with 4 vertices as a subgraph, then this analogous tropical version of the Ceresa cycle he defined is algebraically non-trivial. And as for the l-adic Ceresa class, I just showed you. First of all, we know that it is zero. It is zero for hyperelliptic curves. Well, the reason is because we already talked about if I pick a Weierstrass point as my base point, you can see that the Ceresa cycle is literally 0. And the Ceresa class we just defined is independent of the choice of the base point. Thus, this Ceresa class will actually just be 0 for hyperelliptic curve. And last summer, as an MRC program, joined with Dehn Biscono, Daniel Litt, and Padma Srinivasan, we showed that for genus 7 Hurwitz curve, meaning the genus 7 curve with the maximum possible automorphism group, the Ceresa class is actually torsion. And this is a small list of previous works on this cycle and over this class. And the main result I want to present today is if I take a smooth projective curve over the local field, say double bracket T, which had semi-stable reduction at the special fiber, then the Ceresa class is actually always torsion. And I want to make a remark that, so for this case, because my field is local in C double bracket T, its Galois group is procyclic. And if I call its generator rho, then the cohomology group where the Ceresa cycle lives is actually isomorphic to the co-invariant of rho. And we were able to actually explicitly compute the Ceresa class for such a curve just using the degeneration, the combinatorial data of the degeneration type of its special fiber. So are there any questions at this point about the main theorem? And also let me see whether I'm able to see people raising hands if there are any questions. Okay, if there are no questions, now let me explain why we were able to compute the Ceresa cycle for a curve over C double bracket T just using this degeneration data. Well, the reason is for a curve over C double bracket T with semi-stable reduction, we can actually get the Galois action on its fundamental group just from the degeneration data. And now let me explain why the Galois action on the fundamental group is related to the Ceresa class. So let pi be the pro-L étale fundamental group of my curve C base changed to K bar. And let's define its lower central series. So by lower central series, I mean this is a filtration, a sequence of subgroups of pi, where at each step of at the K+1 subgroup is the commutator of pi with the previous subgroup of L pi. So as you can see, by this definition, each LK+1 pi mod LK of pi is abelian, because because its commutator is in L pi, LK of pi. And it's actually even larger than that. And also, you can see that if I look at the first piece of the associated graded, if I look at L1 pi mod L2 pi, it's just pi mod out by its commutator. So it's the abelization of pi, which from now on we will denote by H. H stands for homology because I have a fundamental group and its abelization should be my first homology. And the second piece, L2 pi mod L3 pi, again, as I said before, it is abelian. And actually, you can see that it is actually isomorphic to the wedge 2 of H mod out this one relation. And this one relation, you can think it as either from polarization or for this étale case from the wave pairing, the symplectic form, or you can think about discrete case. Well, for discrete case, if I have a proper curve, my fundamental group is a free group modeled out by one relation. And this Q, you can think it as the relation arising from there because, yeah. So you can see that if I know the Galois action on H, then I know its action on wedge 2 of H mod Q. So if I look at the short-leg sequence of GK modules, where the first piece is this L2 pi mod L3 pi, the middle piece is L1 pi mod L3 pi, and the last piece is my H. You can see that if I know the GK action on H, I know its action on the first term and the last term, but it does not mean it determines the action on the middle piece. Okay, the middle piece is actually non-abelian, it's a non-abelian group. And by group cohomology, you can get a class in H1 of GK with coefficients harm of the last piece to the first piece, which actually will encode the information of the GK action on the middle piece. This is just from group cohomology. And by the work of Dehn and Matsumoto, this class, twice of this class, actually equals to the Ceresa class we were just talking about. So this means that the Ceresa class actually encodes the information of the Galois action on the second piece of the lower central series of the étale fundamental group of my curve. And thus, if I claim that from the degeneration data of the special fiber, I was able to read off the Galois action on the whole fundamental group, is not, then of course, from this degeneration data, I'm able to compute the Ceresa class. Okay, and in the next slide, I will explain why we can actually get the Galois action on the fundamental group just from the degeneration data. So to do that, we just need to essentially need to understand what's a curve over, say, double bracket T look like. So we can think about algebraic curve over the local field double bracket T as a holomorphic family of Riemann surfaces fibered over a circle. Because the reason is the field is T double bracket T, its Galois group, as we said, is procyclic. So it is generated by one element. And so you can think about that element as going around the circle. And if you consider the monodromy representation of this element, of this action on the fundamental group of the Riemann surfaces, this induces the element in the mapping class group. So what is the mapping class group? Well, the definition of a mapping class group is it's a group of orientation preserving diffeomorphisms up to isotopy. But another way to think about it is the fundamental group of the moduli space of genus G curves, so the pi1 of MT in the analytic topology. And well, another way to think about it is because Riemann surface of genus greater than 0 are Ellenberg-MacLane spaces. So automorphism of a Riemann surface is just, you can characterize it by looking at its automorphism of its fundamental group. So the mapping class group is actually a index 2 subgroup of the automorphism group of pi1 of a Riemann surface. And that index 2 comes from the orientation preserving part. So this also explains why if I have to give a family of curves around a circle, I just need to specify an element of the mapping class group by specify this comes from the monodromy representation of the element acting on the pi1 of the fiber. And of course, in algebraic geometry, the way to say it is, well, a curve over C double bracket T is given by the classifying morphism from spec C double bracket T to MG. Again, because MG is a Ellenberg-MacLane space, you can specify it by mapping mapping the generator of pi1 of C double bracket T into pi1 of MG. So it's again the same as specifying an element in the mapping class group. So I will always keep rho to be the generator of pi1 of the Galois group of C double bracket T, and always call the map S being this classifying morphism, or in other words, from rho to the mapping class group. And since I was talking about the algebraic fundamental group, I really should take the profound completion, but I can, since I'm looking at this one element, it's enough to just look at this discrete mapping class group. Okay. And again, the upshot of this whole slide is that a genus C curve over C double bracket D is the same as an element, as specifying element of the mapping class group. And yeah, but actually for our purpose, we are not going to take any element of mapping class group. We are going to take some special elements, which are particularly easy. We call them multi-Dehn twists. So the mapping class group for closed genus C Riemann surfaces is actually generated by elements which are called Dehn twists around simple closed curves. Now let me explain what a Dehn twist is. Well, I can, first of all, to give a Dehn twist, you just need to specify a simple closed curve. So in this picture here, of this genus 3 Riemann surface, I drew this red curve L, and I'm going to start with a Dehn twist, which I denoted as T sub L. And first of all, a Dehn twist is local. It only acts, its action only happens on a neighborhood of this closed curve L, which I drew this blue neighborhood. I don't know whether you can see it. And again, I'm going to describe the Dehn twist action on the Riemann surface by describing its action on pi 1 of this Riemann surface. And in other words, I just need to describe the TL action on simple closed curves of my Riemann surface. And because the action is local, for example, if I have another closed curve alpha on this Riemann surface that does not intersect L, then the TL will act on alpha trivially because all of the action happens in this blue neighborhood. Okay, so now let me tell you what happens if a curve intersects L. So look at this closed curve beta where it intersects L, and I did draw this this black line segment in this blue neighborhood in the right picture. As you can see, I basically cut out this blue neighborhood of my red curve L in the right. So what a Dehn twist does is you can think that it creates a detour. So previously, I was able to go from the bottom of this blue circle directly to the top blue circle just by this straight line on the left side of this cylinder. But now, after I apply to a Dehn twist, I can't just go directly anymore. I have to take a detour. I have to go around this cylinder. In other words, it's like go around L and then end up at the same point. So this is what a Dehn twist does to my curve, to my simple closed curve beta. And this is in other words, why it's called a twist is because you can think the whole cylinder is twisted around this red curve L. And such elements actually generate the whole mapping class group. And if I have two disjoint curves, L and L prime, then Dehn twist around L and Dehn twist around L prime commute. So by a multi-Dehn twist, we mean that the product of Dehn twist around a set of disjoint loops. And if I have a curve defined over C double bracket T, which has semi-stable reduction at its special fiber, is equivalent to the defining element in the mapping class group is actually a multi-Dehn twist. So this means that to give a curve over C double bracket T is the same as giving this combinatorial data. The combinatorial data, namely a set of loops or a set of isotopic classes of loops L1 through Ln, and also a list of positive integers, which gives you the multiplicity of Dehn twist at each loop. Or so this information can be you can say that on the picture A, this is exactly what I'm doing is I gave you a Riemann surface of genus 3 and a set of 5 loops. Each pair are disjoint. They're not intersecting with each other. And this actually specifies a curve over C double bracket T. And what does its special fiber looks like? Its special fiber looks exactly like you replace each closed curve Li by a singularity. So on the right-hand side, the picture B on the top, you can see that this is the special fiber if you consider it as a singular curve or a singular Riemann surface over in the complex topology. You can see that each closed curve Li is replaced by a singularity. Okay, and from here we can also draw the dual graph of my curve. How do you do that? Well, one way to think about it is each is a finite metric graph where each vertex corresponds to a connected component. So imagine my Riemann surface in picture A, and imagine you cut around each closed loops Li. And then you can say that this Riemann surface will be cut into 3 pieces. One piece has boundary L2, another piece has boundary L2, L3, L4, and L5, and also this L3, L4, L5 form a third piece. So each connected component gives you a vertex. So in this dual graph, as you can see, I have 3 vertices. And each edge corresponds to a closed loop in my previous Riemann surface. So, and I didn't assign multiplicity around each of the Dehn twists around each loop. If I do, each of the AIs actually gives the edge length of my metric graph. And also the vertices can be weighted in the sense the weight corresponds to the genus of this connected component, this subsurface. But in the picture I drew here, each vertex has weight 0. As you can see, each of my subgraph has genus 0. Okay, so this combinatorial data is enough to specify a curve over C double bracket T. And also from the previous slides, if you remember, I'm trying to explain that why from this combinatorial data we actually can recover the Galois action on the fundamental group. And as you can see from this dual graph picture, what I can actually recover my Riemann surface together with this set of loops. In other words, I can recover my Riemann surface with this element in the mapping class group, and the mapping class group acts on the fundamental group. So just from this dual graph, we can actually recover the Galois action on the fundamental group. And yeah, right. Okay, so with this data, we can explicitly compute the action of S of rho on pi 1 of sigma g and get a cocycle element that's representing the Ceresa class. And this is the tropical perspective, as I was saying, because a tropical curve can be given as a finite metric graph with weighted vertices. So so this whole notion this whole computation of Ceresa class can be carried out just by given the input as a metric graph or a tropical curve. Okay, so let me give you an example. So for example, if I give you a Riemann surface of genus 3 with 6 closed curves, these 6 red curves as I'm drawing here, each with multiplicity 1. So consider Dehn twist, the product Dehn twist around each loops with multiplicity 1. And this specifies a curve over C double bracket T, as we talked before, and whose special fiber has dual graph, this K4, the complete graph with 4 vertices. And we were able to compute that the Ceresa class for this curve is non-trivial, and it is as the main theorem suggests, it is torsion, and we were able to compute that its order is 16. And actually the fact that the Ceresa cycle here is non-trivial shows that the Ceresa class is non-trivial shows that the Ceresa cycle is rationally non-trivial. And this agrees with the notion of the tropical Ceresa cycle from Jarkov and his result, where K4 has algebraically non-trivial Ceresa cycles. Okay, so this is the example we were able to compute. Okay, so now let me explain how to compute the Ceresa class for curve over C double bracket T and the proof of our main theorem. So, well, before we try to compute the Ceresa class, let's first compute the cohomology group where this class lives in. And again, from now on, I'll just be working with the discrete topology because, well, there's a comparison theorem and you won't lose any information actually just by looking at this topological data. So let me define H from now on to just be the first singular homology for a Riemann surface of genus C. and Q is represents the fundamental class, or the symplectic form on the first homology. And let L be the wedge 3 of H mod H wedge Q. The reason we want to mod out H wedge Q is because we want our class to not be dependent on the choice of a base point. Or in other words, is we want to work with the mapping class group for a closed Riemann surface instead of a Riemann surface with a boundary component. And you can also get this coefficient by looking at the Berman sequence there explicitly. Okay, so the Ceresa class lives in the cohomology group. So now you can think it as group cohomology given by H1 of Z. Well, it's a cyclic group, free cyclic group generated by one element rho with coefficient in L. And again, this is isomorphic to a co-invariant L mod out the S of rho minus identity x on my coefficient group L. To compute this group, this means we need to know how a multi-Dehn twist acts on the homology of a Riemann surface. Well, we already know what a Dehn twist does to the fundamental group. So of course we know what a Dehn twist does to the underlying homology class of any closed curve. So let's define IAB as the algebraic intersection number of two classes in the homology. Then if I have a Dehn twist T around L with multiplicity A acting on a homology class, which represented by a closed curve L prime, and it actually the output will just be L prime plus A times the intersection number between L prime and L times the class represented by L. And the reason is, so first of all, we know that if L and L prime do not intersect, then the Dehn twist action should be trivial on L prime. And if it intersects, well, remember the detour picture. So it's actually kind of visible that if they intersect once, then the homology of L prime need to be replaced by L prime around, also you went around L. So that's an intuitive way to say why how a Dehn twist around a single curve act on another simple closed curve. It's just by thinking about that detour picture, you are replacing the class represented by L prime now by L prime plus the extra going around the circle part of the cylinder. Okay, and now let's look at the multi-twist. If I have a product of Dehn twists, then because for each Li and Lj, the Dehn twists commute with each other. So, so it doesn't matter first of all, it doesn't matter the order. And also you can directly say that, and also because they're disjoint, when I compose them, I wouldn't get extra classes coming from intersection numbers between Li and Lj's for Ij in 1 through n. What I will get is just, again, this L prime and with the summation of some classes of Li's. Well, Li's are the curves I'm doing Dehn twist by. Okay, so from here you can observe that so we can observe that this means if I take the multi-twist minus identity acting on Li, I can move this Li's term to the left side. What happens is its image lies in the span of the homology classes given by the Li's, while the Li's again are the curves we're doing Dehn twist by. And again, because each of the Li's intersect are disjoint, we know that if I apply this this multi-twist minus identity again, I will get 0. Yeah. Okay. So from these slides, first of all, from these slides, we know the action of a multi-Dehn twist on the first homology of a Riemann surface. We know how to compute the cohomology group where the Ceresa class lives in. And also we learned that the action of the multi-Dehn twist minus identity squared is actually 0. It's trivial on the first homology. Okay. And this observation gives us a nice filtration on wedge 3 of H. So now let me define Y to be the kernel so let me, from now on, I'll just have delta to be my multi-Dehn twist, just to make the notation easier. And I'm going to define Y to be the kernel of delta minus identity. And so this subspace Y gives me a filtration on wedge 3H by the first term. The first filtered piece is just itself, wedge 3H, and the zeros piece is wedge 3H, and the first piece is Y wedge H wedge H. This is the subspace of wedge 3H, sub Z or sub Z module. And the second piece is Y wedge H, and the smallest pitch will be the third wedge of this sub Z module Y. Okay, and because from the previous page we learned that delta minus identity acting on H is 0, this shows that the image of delta minus identity is in the kernel of delta minus identity, namely Y. So this shows that the action delta minus identity actually maps a filtered piece to a deeper piece. Okay, so this means that okay, and moreover, we were able to show the we were able to actually compute the image of delta minus identity and get more information. We were able to show that the second piece, F2 wedge H, actually lives in the image of delta minus identity when it acts on the whole wedge 3 of H. When it's tensor with Q, it's when tensor with Q, it lives in the whole image. So equivalently, if I'm looking at the integral structure, this means that the induced map from the second piece to the whole cohomology group lies in the torsion subgroup. Okay, so remember our main theorem was we want to prove the Ceresa class of a curve over C double bracket T to be of is torsion or to be of final order. So now what we need to do is we just need to find a representative of my Ceresa class. Well, and if I can find a cocycle that lives in the second filtered piece of wedge 3H, then that shows using this lemma, we know that the Ceresa class is actually of torsion. Okay, so the next slides will be explaining how do I find a cocycle or the image of delta mapping to wedge 3H, which lies in F2 wedge 3 of H. Okay. So to find such a cocycle, I need a morphism called the Johnson homomorphism. Well, so again, let gamma G be the mapping class group for closed Riemann surface of genus G. And because we know it acts on the first homology and it respects the intersection pairing, so actually it has a symplectic representation from gamma G to SP of H. It's orientation preserving, so it's SP. And the kernel, and it's actually surjective. And the kernel of this map is called the toriadic group. And the Johnson homomorphism is a group homomorphism from the toriadic group to wedge 3 of H mod H wedge Q. So because I'm looking at the mapping class group of a closed Riemann surface instead of having a boundary component. And the reason Johnson was starting this homomorphism was because this homomorphism captures the free part of the urbanization of the toriadic group. So if you look at the urbanization of a toriadic group map under the Johnson homomorphism, the torsion is actually, the kernel is actually of torsion. So the whole free part was captured by this homomorphism. And Morita, and you can say that the image of this homomorphism actually is the same as the coefficient we had for our cohomology group before, for the where Ceresa class lives, and it is not a coincidence. So Johnson defines homomorphism from toriadic group, and the Morita tried to extend this homomorphism to a cross homomorphism to the whole mapping class group, but it actually doesn't tend directly, and he had to actually. he had to enlarge the coefficient by a half. In other words, is the Johnson homomorphism itself not necessarily get extended to a whole mapping class group, but twice of the Johnson class does. Okay, so and by the work of Hand and Matsumoto, the twice of this Morita class actually exactly equals to the Ceresa class of the curve over C double bracket T. That's why I was saying that the image, or sorry, the target of the Johnson homomorphism is the same as the coefficient as the Ceresa class. That's not coincidence, because the Morita class and the Ceresa class are essentially doing the same thing. And also this can also be explained by, if you look at the explicit construction of Morita, you'll see that what he was really, like what information it really has is, again, exactly the Morita class measures the mapping class group action on the second term of the lower central series of the fundamental group of a Riemann surface. So they are really doing the same thing. So, okay, so, but from this Johnson homomorphism, we were able to actually find a nice representative for twice of the Morita class. Okay, so how do we do that? Well, because from the previous slides, we know that the symplectic representation of the mapping class group is surjective. So gamma G is surject onto SP of H. So so that means there exists element tau in gamma G, which acts as -1 on H1 on the first homology. And we call such an element a hyperelliptic involution. And if I take any of such element tau and take an element gamma in the mapping class group and consider its commutator. So first of all, because when you look at its quotient in the symplectic group, -1 lives in the center. That means the commutator gamma tau actually will live in the torelli group. It will act trivially on the first homology. And so we can apply the Johnson homomorphism to it to get an element in wedge 3H, to the quotient of this wedge 3H. But actually, it doesn't matter which representative in wedge 3H we pick. And from now on, actually, I will just be using a representative in wedge 3H to denote the Johnson image. And actually, by direct cocycle computation, you can see that the Johnson image of this commutator represents exactly twice of the Morita class of gamma. And when gamma is our multi-Dehn twist, that means the Johnson image of this commutator exactly represents our Ceresa class. And now all we want to do is to show that it doesn't matter which multi-twist we're taking, the Johnson image of this multi-twist always lives in the second filtered piece of the wedge 3H. Okay, so first let me give you a simple example of the story. So consider if my delta is a single Dehn twist. Let's say the Dehn twist around a simple closed curve L, this blue L I'm drawing here. And consider the hyperelliptic involution tau as flipping this Riemann surface. Or in other words, mapping, you can see mapping L to tau of L, and I draw a orientation on L to make it even cleaner of what tau did. Okay, so then the commutator of TL with tau, you can, when you explicitly write it out, you can see that it actually is the same as the composition of the Dehn twist around L, and the inverse of the Dehn twist around tau of L. And Dehn twist around L and Dehn twist around tau of L, because L and tau of L are disjoint, you can see that if I cut around L and I cut around tau of L, this surface will be split into two subsurfaces. So such a pair of curves are called bounding pairs. And elements in the torelli group, which are given by the form TL and T of L prime, where L and L prime form a bounding pair, its Johnson image is exactly can be represented by the homology class of L, wedge omega, where omega is a symplectic form of a subsurface a subsurface with boundary L and this top L. And actually, when you pass by the quotient of, instead of looking at wedge 3H, if you look at wedge 3H mod H wedge Q, what this quotient did is it quotienting out the choice of which subsurface you pick. Okay, so yeah, but in here, as I said, it doesn't matter which representative we pick in wedge 3H. I'm just going to pick the one on the left. As you can see, the symplectic form for this subsurface can be written as alpha 1 wedge beta 1. Yeah. So the Johnson image can be represented here as the class of L wedge the class of loop represented of loop alpha 1 and the class represented by beta 1. And as you can see, my Dehn twist T of L acts trivially on itself on L. It acts trivially on alpha 1 because L and alpha 1 doesn't intersect, and the same L and beta 1 doesn't intersect. So the Dehn twist TL actually acts trivially on all of these three classes. So not only it lives in, not only this element lives in the second filtered piece of wedge 3H, actually lives in the third piece, which actually the third piece in this case, this whole F3 of wedge 3H lives in the image of delta minus I, is trivial in the co-invariant. So actually this means that the Morita class, or twice the Morita class for a single Dehn twist is actually trivial, just on the node trivial. And another way to say that is, oh, actually also let me explain a little bit, which is a change of coordinates principle. So the point is I want to say that it was not special about the curve L I picked or the hyperrevolution tau I picked. So the change of coordinates principle said that if I have any two non-separating closed curves alpha and beta on a Riemann surface, there exists a homeomorphism sending alpha to beta. So if I have a Riemann surface with a non-separating closed curve, it doesn't matter which curve I pick because homeomorphically they're all the same. And the reason is if you cut along that curve, you get a Riemann surface with two boundary components, and all of such are homeomorphic to each other. So this means if I have any single Dehn twist, I can just move my alpha up to homeomorphism to the loop which I drew for you. And because we have the freedom to pick the hyperevolution, so I can pick the tau which I drew for you in the previous slides. And this shows that the twice of the Morita class for any single Dehn twist is trivial, just on the nodes trivial. Another way to think about it is you can even move your curve to a closed curve that is fixed by your hyperevolution. That way it's more visible that your Morita class or twice the Morita class is trivial. Okay, but that is the case of a single Dehn twist. But the real story is we want to deal with multi-Dehn twist, product of Dehn twist around disjoint loops. So first, we have a lemma which reduces this case to dealing with each term. So let tau be a fixed hyperevolution. And if the Johnson image of each TLI, the commutator of each TLI with tau lives in the second term of the filtration, then the Johnson image of the commutator for the product of all the TLIs and tau will also live in the second piece. And this can be shown inductively, essentially, well, we know that the Johnson homomorphism is a group homomorphism. So we can actually write out what this commutator of the looks like for the product. And you can inductively show that the Johnson image equals to a summation over I with some element Gi in the mapping class group acting on the Johnson image of TLI with tau. But Gi actually acts trivially on Y, and which means that it preserves the filtration. So thus, this summation will, if each J of TLI tau lives in the second piece, then this whole sum will still live in the second piece. So this means that we have reduced our problem to computing the Johnson image of a single Dehn twist around a fixed hyperelliptic evolution. So it is actually, this is subtle that it is different from what I was describing before, where for a single Dehn twist element, the Morita class is trivial, because here we are not computing the Morita class of a single Dehn twist. We are computing the Johnson image. We are not allowed to change the choice of the hyperevolution, or we are not allowed to move where my curve is. Okay, so this is not picking a representative anymore. This is a fixed element in the mapping class group that in the toradic subgroup of the mapping class group that I want to compute the Johnson homomorphism of. And as you can see, what we want to happen is that for each element, it looks like a bounding pair. We want to say that it doesn't matter what tau is or what L is. The image of a Johnson, the Johnson image of the commutator will be somewhat similar to the Johnson image of a bounding pair. And what is a bounding pair? I should actually explain a little bit more. The bounding pair is I have two curves which are homologous to each other and disjoint and homologous to each other, and then the Dehn twist around L and the inverse of the Dehn twist around the other. This is the bounding pair. So the difficulty we'll face is exactly the picture I'm drawing here. Consider L being my blue loop, and tau is still the hypervolution, which is given by rotating my Riemann surface. And you'll see that the problem, well, the L and tau L, because tau acts as -1 on the first homology. So L and tau L will be homologous, but the problem is the intersect. As you can see, the red curve is exactly the image of L under the involution tau. They intersect at 2 points. And there's no, and you can't make them not intersect by any homomorphism or, yeah. So, so in this case, L and tau L are not a bounding pair because they intersect. And the solution we found is we take a third curve, L prime, yeah, and where you can see that L prime and L and tau of L are all homologous, because you can try to visualize it. If you cut through L prime and cut through L, you will see that the Riemann surface will be cut in 2 pieces, and they are the exactly 2 boundary components. This shows you that these 2 closed loops are homologous, because I mean, well, they are the boundary of a 2 cell, right? Okay, and also L prime does not intersect tau of L. So we can, instead of take T of L times directly T of tau of L inverse, we put T of L prime inverse and T of L prime in the middle. And now I wrote this commutator as product of 2 bounding pairs. So because each L and L prime and inverse and T L prime and T tau L inverse, these are bounding pairs because each pair of them don't intersect. So I wrote them as products of bounding pairs. And now if I apply the Johnson homomorphism, you'll see that actually the Johnson image of a bounding pair will always lie in the second piece of the filtration on wedge 3 we gave. And so now all we need, well, the last piece of the puzzle is exactly to show that for any pairs of L and tau L, we are able to find such L prime without drawing a picture. And exactly Andy Portman proved such a result in 2008 for us. So, so his result said that if genus is greater or equal to 3, and if you have two homologous non-trivial simple closed curves, L and L prime on Riemann surface, then there exists a sequence of closed curves, Li's, of non-trivial, these are all non-trivial simple closed curves, such that each pair Li and Li plus 1 are disjoint. And also all of them are homologous to each other. Thus, we can always write the commutator of our TL with tau into products of bounding pairs. And then when I take the Johnson image, well, because the group homomorphism will just be a summation of the Johnson image of these bounding pairs. And because each element of them lies in F2, their sum also lives in F2. And with this last piece of the puzzle, we finish the proof of our main theorem. And that's all I want to talk about. Thanks for listening. And here's a reminder of what we proved. Namely, if I have a smooth projected curve over the local field C double bracket T with semi-stable reduction as a special fiber, this Ceresa class is always torsion. And we prove that by using lots of topology. Thanks for listening.
And everyone else should feel free to. There's also a clap button if you feel like doing that. So we're getting a lot of visual claps. All right, great. Thank you so much, Wanlin. That was great. So now let's open the floor to some questions. So the easiest way to do that is probably to raise your hand by clicking the raise hand button, or to type into chat right now. So does anyone have any questions they would like to ask?
Okay.
Pause a bit.
Daniel, can you actually unmute them? I can't find. I saw people raising hands, but I can't find.
Oh, I see. So Alex Betts is raising his hand.
Yes,
so,
I can't find their name in the list of participants. If you see them, can you?
I can call on them for you.
Thank you. Thank you.
All right. Let's see. Will has already unmuted himself. So Will, would you like to go ahead?
Do you have a sense of what the order of this torsion class is? Like, is the order, is it only going to be plotted to like small primes relative to like the AIs, or could there be very, very big primes in the torsion order?
So this is what we are actually currently working on, is explicitly bound the order. And the sense currently I got is it can be any number. That's cool. Yeah, I think so. At least at this point, we don't seem to be able to say that you can only restrict to powers with small primes. Yeah.
Great.
All right, thank you, Will. Looks like Alex Betts also has a question. Alex, do you want to unmute yourself and go ahead?
Hi, yes. So my question was about this Hein-Matsumoto theorem you had, saying that the Ceresa class can be computed in terms of this extension coming from the depth 2 part of the fundamental group. So in this case, saying that this class is torsion, is that somehow the saying that this extension, non-abelian extension that you have should become split when you take the like the Malchev completion or the Malchev-Li algebra of this extension of groups?
I believe what you said is correct. Yeah,
okay.
I think so. Yes.
Yeah,
well, yes. I mean, well, being torsion just means it's rationally trivial, right? And when you are working with Lie algebra, you are working with, I think, over probably a field or Q, or right. I don't know what's the base of the Lie algebra you're taking, but yes, that means it's trivial in that sense. Yes.
Okay. Thank you.
All right. So some enterprising people in the audience created a Google Doc to ask questions and discussions, and there are a couple interesting questions from the Google Doc, mostly from anonymous people. But do you mind if I ask a couple of those?
Sure. Go ahead.
So an anonymous person, who should feel free to de-anonymize themselves, asks if the Ceresa class is always torsion, like maybe over other fields, not C double parentheses T.
So for this étale version, this L-adic Ceresa class, we don't know any example that it is not torsion. But for the Ceresa cycle, where people constructed differential forms and use harmonic volume to show that or in other words, the Betti realization of the Ceresa class in the intermediate Jacobian, there are examples where that class is actually of infinite order. And I believe the result of Kandari and Morita, they show that for the Feynman curve where n has prime divisor greater or equal to 7, their Ceresa class in the Betti or Hodge realization is actually of infinite order. But for the étale version, we don't know. At this point, at least I don't know.
I have a comment on that, if you don't mind. So I think if you look at the generic curve over the generic point of MG, the fact that the Johnson image is not torsion implies the Ceresa class has infinite order.
Right, makes sense. Yeah, thanks, Daniel. Yeah.
Okay. All right. Are there any other questions? Including, so let's see. There's a lot of questions from chat, but from the Google Doc, but I think they've mostly been answered by people. So let's pause for one more minute to give people a chance to raise their hands. And then if there are no more questions, we can thank Wanlin again. All right, let's clap for Wanlin again. Okay, and 25 people are clapping silently. All right, thank you so much, Wanlin. Let's take a 20-minute coffee break. Unfortunately, we can't have coffee together in person, but we can, continue to chat in the chat room, and then we'll restart at 1:15 p.m. Eastern Time, so in 20 minutes, with Padma Srinivasan's talk. Yeah, so with that, I'm going to mute myself and see you in 20 minutes.